All right. So yeah, hi everyone. My name is Sanjay, and I'm a PhD student at UC Santa Barbara. I'm working with Arpit Gupta, and this is a work that I've been doing towards inferring QoE from active and passive measurements. So to start off, just kind of like a high-level motivation of this direction of research. So yeah, assume like you kind of have like Alice who's at the library, and for example, she's using a video conferencing application such as Zoom, and she's getting good quality of experience. She's on a call with someone, and things are okay. Then comes along Bob, who sits by Alice and connects to a similar access point, and the same access point as Alice, and starts a Netflix session. And so let's just say Netflix is a streaming service that tends to be aggressive on startup. Maybe it causes some kind of congestion that eventually gives Alice some kind of freeze frames, like rebuffering, or downgrades her quality of service, right? So as a result, Bob is having a good QoE, Alice is having a bad time, and this is because in the current setting, applications don't exactly have like full visibility of the network, right? And in general, applications are just trying to optimize for their own performance, and because they obviously want people to like subscribe to Netflix, right? Or use their applications. And so, but like who else is QoE important for, right? It's also important for ISPs, right? Because ISPs, in cases where they actually have competition, they actually want to win over customers, right? So as a result, they want to be able to better support applications that their customers want, right? So since ISPs have visibility, the kind of main idea or the research drive was like, can we do better, right? Can we work towards something better? And so in an ideal world, like if we understood the indicators for how QoE QoE degrades, could we actually schedule packets to provide better overall QoE for the entities involved, right? And so like to this end, like the first question I aimed to understand was, how are video streaming and video conference applications like affected by congestion in the wild? So when I first started this problem, like a year or so ago, like I was definitely using some very like emulators like Mininet, and like traffic control to try and simulate what these applications were experiencing, like especially during like COVID time when we're isolated. I was like just doing like lab setups, and I noticed that like over time, like it's kind of shown that like these lab setups aren't like high fidelity, and we may not actually induce like situations that actually occur in the wild. Like we may not be like developing solutions that are aware of like the actual problems in the wild, right? So then the drive for me became like, can we actually use the UCSB campus network as a test bed for this kind of research? And with the great support and help of the network IT staff, we are like able to actually like use the campus network to generate high fidelity data that we can then try to analyze for these kind of congestion events, and also with our own devices, see how we're affected, how the QoEs of applications are actually affected. So as a roadmap for this presentation, I'm focusing on two research questions, which is basically how often are UCSB hosts affected by like latency inflations? And so I'm referring to like downstream latency inflations like within the actual campus network. And so like how frequent are these latency inflations and how long do they actually last? So in the sense of like how, in a sense like how much can like active measurements actually detect these kind of things, and how much applications actually need to like repair for or like recover from. And then as kind of like a case study with the active measurement setup that we've been developing, I was looking at the relationship between last mile latency inflations and the QoE degradation for Google Meet, right? So is there like a relationship, like do we see QoE degrade when we notice the latency inflations, right? So yeah, that's kind of like the roadmap for this presentation. So kind of going over the passive measurement setup real quick that we use, just so everyone knows the data I'm working with, because in the focus for my project was kind of using the campus data still, but I'm trying to draw insights that I can then apply, or then like, at the end, I'll try and tie into what we can, learn for active measurements for the MLab data. So The campus testbed that I used was, UCSB's campus network. So we're basically capturing at the border router, we see all the traffic coming in and out of the network. There's basically a network tap mirroring packets to our own programmable switch that's then anonymizing the packet IP and headers, so that basically the privacy of any users isn't leaked. And also it's removing payload and just preserving like SNIs so we can still identify services, and DNS so we can get that kind of stuff. So that's kind of like in another paper, just a reference in the network that's from ONTAS. And then also we basically use TCP dump on each interface of the server. We're load balancing around like a 10 Gbps traffic load over 4 servers. So yeah, on the active measurement side, I was kind of working similar to like what Lai mentioned about Murakami and Netrix. We're kind of using just a similar model of like deploying Raspberry Pis on UCSB's campus. And the goal of this is, since we have the passive data, we're trying to actually simulate hosts where we can get ground truth now and actually measure the QoE for conferencing applications, right? So we can see how they're affected by different inflations. And so, yeah, so we're deploying these Raspberry Pis with the idea of just like leaving them in a place and like acting like, hosts that can turn on and off at our command. So we're using the salt stack for management. It's pretty simple. It just, executes our commands remotely on all these devices. It kind of gives you full control. And then we use Selenium for automation. So there's some engineering basically to be able to automatically start and like join like Google Meet sessions and like getting past some bot detection. Yeah, ideally also on these end hosts, we can run NDT tests. We can basically capture actual packets, and so some of the next steps I'm working on is like trying to break down the last mile RTT into like upstream and downstream. So yeah, we can do a lot of things at the end host. So the goal of the active measurement test bed is to be able to actually control hosts within our campus where we can get ground truth. So moving on to the data that I use for this analysis that I'll show. We looked at 4 hours of traffic at like a 10 Gbps rate. So it's for basically around 54,000 unique hosts, 90 million flows, 16 billion packets, all connecting to actually, like a million unique hosts almost. And so we also using Amon, which is like kind of Aruba's like advanced, Aruba's like monitoring data. You can basically also get like an access point and a building mapping, so for all of these hosts. And so we kind of were able to look at these hosts over 4,000 access points over like 250 buildings. And so on the active measurement side, just discussing some quick limitations, we were trying to scale the setup to have like hundreds of hosts. There were limitations at the start of the year due to like a lot of the shortages in chips. Raspberry Pis became like, very hard to buy in bulk and from like different sellers. So I kind of had to go on Amazon to like single sellers and buy them. And also like setting up PoE for these devices and getting them installed on campus before like students actually left. So yeah, we basically had about like 25 like Raspberry Pis. We kind of like started off with where we were like trying to get some data from and are currently deployed, but we're trying to scale that up. So yeah, so looking at this data, once we collected this passive data, I was kind of working with PCAPs, and what I wanted to do was convert this to what I mentioned, like latency inflations, right? And so what my methodology was basically calculating the downstream RTT for each TCP packet. So very simply, what I'm doing is for any TCP packet, I'm just matching the time that the actual data packet enters the network with when its corresponding ACK reaches the outside network, right? So I'm measuring that RTT within the network. Ideally, I would like to break that down into downstream and upstream, like I mentioned, but for the sake of this analysis, I'm just using that full RTT, which combines the downstream and upstream, right? And so this figure, it may be a little like over labeled, but what it's ideally trying to do is just show you like what the setup is and the actual times, right? So there is like a slight time between when the packet actually reaches the border and when we actually get packets at our switch, but ideally this time should be constant because it's like a switch to switch. Yeah, this should be like constant and at line rate. So yeah, this should still be a good proxy of the actual last mile RTT, since last mile RTTs are in the order of milliseconds, and like this time would be in the order of microseconds. So yeah, based on that simple methodology of just matching RTTs, I had to sanitize the RTTs a little more to make sure that I wasn't these were actual proper representations of the last mile latency, because there are features of TCP that cause ACKs to be delayed and not actually be measuring the delay in the network, right? And so, yeah, the few things that I had to deal with were like delayed ACKs. First off, I could basically only take RTT samples from packets that were full size. Additionally, like if the push flag is set, that indicates that the application should immediately process it. So those packets also we were able to get RTT samples from. We didn't miss out on the selective ACKs, so we do have some missing RTT samples that we could potentially get using the selective ACK behavior in TCP. And additionally, we had to like remove all RTT samples from retransmitted packets, because yeah, these are basically faulty samples. These two pictures, I mean, this is kind of a general thing. Like in TCP, you're not supposed to use retransmissions for estimating RTTs. That's a common thing, but like these two cases kind of like illustrate why you shouldn't. But yeah, so in the left case, one RTT seems like is the correct, the retransmission is the correct match, and in the right case, the original packet is the correct match, but like you don't actually know. Right? So, yeah. So going on, like I said, we use the Aruba advanced monitoring data to actually get a breakdown of what the access point, the room or building each of these hosts were in, to kind of get more of like a spatial mapping of our hosts. And so Aruba also offers like Airwave, which is kind of uses like SNMP polling for this. But this was kind of like too resource intensive for us. So we kind of used like a hacking method of just processing like plain text messages sent between the wireless controller and the wireless access point, which basically would just let you know when a host roams to a new access point. So you can kind of get an IP to access point mapping. And so we just kind of like maintain this mapping whenever we were capturing traffic. There is like some sort of like issue with the software that I'm working with IT to kind of resolve, but we're only able to get like 43% coverage of like hosts. Like I'm not sure why. Like all access points seem to be showing, but like some hosts like don't have plain text messages associated with them. So that's kind of like being debugged. But we did get like reasonable coverage so we can kind of like break down some of the latency inflations we saw, how they were spatially located. So yeah, so getting on to like kind of like this idea of latency inflation, right? So so yeah, we definitely saw like basically to summarize, like at first when we were looking at the raw RTT values in the data, we saw that maybe about like 5% of them had like were heavily inflated, right? Like the RTT in the last mile was over 100 milliseconds. So like that means like the one-way latency would be like 50 milliseconds, which is pretty significant for just that last leg, which technically, yeah, you could add like 30 40 milliseconds on top of that for traveling higher up in the network. But yeah, so to basically understand the like idea of like where this congestion is occurring and like what these things are, we had to like kind of define what like latency inflation is. So we kind of like made a definition of ephemeral congestion, which is like short-lived latency inflation events, where we kind of like look at like a certain percentile of RTT values exceeding a threshold, right? And so this is kind of like based off of like just literature that I was looking at that kind of like analyze the RT, like the like basically the needs for certain applications, right? So like video conferencing, like if you see basically last mile inflations of like 40 50 milliseconds, then like that could significantly impact like the quality of experience for applications, right? So that was kind of like the idea that like people say the percentile of latency matters a lot more, like maybe like 99 is like much more important than just like the max value or the median value, kind of was like the idea. So yeah, this is kind of like the methodology. So we kind of like look to like set parameters for yeah, this detection. And so we use like a sliding window of 10 seconds Whenever we're reporting percentiles, it only made sense to have at least 100 samples, because percentile is kind of meaningless otherwise. So yeah, that's kind of like the way we went. If you have less than 100 samples, or if you have like 10 samples and you're reporting like the 99 percentile, usually you either report the highest, the highest -1. So you don't know how many samples you're actually getting. And we actually were trying to look for latency inflations that can significantly impact the application, right? And applications have some kind of recovery mechanisms already built in, but so that's why we kind of wanted to have at least enough samples where the percentile is meaningful. So the bottom is just kind of illustrating the sliding window mechanism. So window 1 is basically predicting a latent, the window for time equals 10. At 11, you have window 2. At 12, so you're looking at basically the past 10 seconds sliding window of packets and computing the percentile RTT for that sliding window. So to kind of understand what percentile RTT to use, yeah, we kind of just zoomed in on different hosts. And so this is just kind of indicating how the max or the median kind of don't exactly aren't the right exactly signals to capture this representation of latency inflation. And so yeah, max is too noisy, and median isn't actually going to be sensitive enough to issues. And so that's why 95th percentile was kind of where we zoned in on. A lot of literature actually says 99 percentile is kind of what's more important, but that's for the single flow. For this methodology, we're just kind of looking at the 95th percentile of all packets for a host. So that's kind of maybe why 95th was a little better, but yeah. So again, we're not going to predict anything for sliding windows that have less than 100 samples, because there's not enough ground truth. We use a threshold of 100 milliseconds. Again, this was kind of empirical. From this graph, you can kind of see that 100 milliseconds is generally within definitely yeah, that's when things are going to be definitely significantly impacted, right? You're going to have if you have 100 millisecond RTT, that means 50 milliseconds latency either way, just in the last mile. So your whole RTT is likely over 100, 200 milliseconds at least, and so yeah, this graph, each data point is just a single RTT packet for a single host. You can kind of see 100 millisecond threshold. So yeah, kind of getting into the actual latency inflations that we saw, how they existed in the network. We saw that basically more than 100 hosts are experiencing an ephemeral event at any given time. And so these are kind of spatially, yeah, these are located in different buildings. Yeah, this problem is not basically localized to a single area. It's this problem is actually occurring. And for example, just to kind of zoom in a little bit on that graph, these kind of latency inflations kind of exhibit this cluster and cluster property, where there's only a certain subset of buildings that are kind of experiencing this congestion, and then out of those subset, there's only a subset of access points in there, and a subset of hosts, and out of the active hosts at that time window. So yeah, this problem is kind of localized, so maybe there's a way to actually predict or understand the right way to kind of monitor for these kind of issues at the access point level, or yeah, that's gonna be it. Looking at kind of the duration, or the duration between different ephemeral events. This graph is basically a CDF that shows yeah, the duration of how long these latency inflations are actually lasting. So what this graph kind of the takeaway, I think, is that the ephemeral events are actually very short-lived. So these latency inflations just last for less than 10 seconds, could be wireless issues. I definitely want to go further into debugging causes, whether it might be queue issues, or being able to understand which ones are wireless issues versus queuing issues. Yeah, just as a side note, the green graph, the green line is basically the duration between different ephemeral events, right? And so the idea here was, if this is also heavy-tailed in nature, then maybe that there's a way for us to say that there's a certain subset of hosts that are more likely to experience an ephemeral event because they've experienced one recently in the past, right? So it could just kind of help with that predictability nature. And so this is kind of because like we only captured for an hour at a time. So in general, like this duration is skewed toward 1 hour. So if we captured for a longer time, I believe that this would also be like more heavy tailed, but we definitely see that the ephemeral event duration is like heavy tailed. Yeah, and so this is graphed again on like a log scale. So yeah, CCDF, not a CDF, I'm sorry. And so yeah, I just went over, and I know I just went over a lot of methodology. And so real quick, just the idea of this table is just to give a little more confidence in the idea that like I've picked parameters that are not skewing these results. And so yeah, what we see here is I computed basically the slope of this red line when I slightly perturbed a single parameter in for each row, right? So the idea is this distribution still stays heavy tailed, even though the parameters are slightly changing, meaning I haven't picked parameters that are overly skewing my results, right? So that's just trying to give a little more confidence. I know I just went over a lot of methodology really fast, but yeah. So yeah, so in general, I think like the takeaway here from like the passive data is, yeah, these ephemeral events are, definitely occurring, and they're occurring. They're basically latency inflations are occurring at a large enough magnitude to actually impact the QoE of applications. And so it's something that we should definitely be like, concerned about, or like at least be able to try and understand how to measure. Yeah, it's very heavy tail behavior. So to kind of move on to like the like second research question, more like kind of towards the QoE, we kind of wanted to understand how we could, we wanted to understand how the QoE of applications is affected by these latency inflections, like how much do they actually matter, yeah, like, or do applications correct well enough for them? Are there better indicators that we should be looking for to understand the QoE degradation? So again, we use the Raspberry Pis that we deployed on our campus to run video conferencing sessions and record the QoE of applications. We use the Salt Stack to manage and script experiments, and Selenium for automating the browser, as I mentioned before. And what we did was measure the QoE using WebRTC stats. So for Google Meet and Teams, you can actually get some useful stats out of the WebRTC. For Zoom, unfortunately, it seems to use a different format, so you can actually get you can actually get meaningful QoE. But what we can get from Meet and Team sessions are the FPS, the drop frames, and the freeze frames in a like data format, right? So this is useful because we can automatically record the QoE from our Raspberry Pis and get an indication of how the session went without having a physical user watching or running a session. And yeah, so to kind of give a little insight into the results, this was kind of just a case study for the relationship between latency, inflation, and QoE degradation. So yeah, this is, I definitely hope to scale up this experiment. I'll just start to say, I definitely hope to scale up this experiment. This is just a single Google Meet session that I'm showing right here. We kind of ran this right during finals time, right when students were leaving. This was like, just like a test run we were getting as we got our setup out. And after students have left, there's actually not much congestion because it's like summertime. So it's been hard to like scale up this experiment. But for this, yeah, for the sake of this slide, we're talking about a single Google Meet experiment, a Google Meet session that was run for 15 minutes. So in the top left graph, right here, we're basically looking at the, you guys can see my cursor, right?
Yeah, we can.
Okay, yeah. So the top left is basically showing the raw RTT values for that one host that joined a Google Meet session. So first off, Google Meet uses heavily UDP traffic, right? So that's also an inherent limitation of this methodology, and something that is a future work is how we can extend this better to hosts that are mostly sending UDP traffic. So this this host still has sent basically around about, I think, 75 to 80 TCP samples in the 15-minute time window, right? So we can see the raw RTT values for each of these for each of the packets. And so there's definitely some significant inflation above 100 milliseconds a couple times, one during startup, probably when, resolution is being fixed. And later on, we see one around like 500 seconds. And so in the other three graphs, we see the QoE for three metrics for the Google Meet session, right? So the FPS, we see the cumulative drop frames, and we see the amount of like freeze frames or rebuffering for the Google Meet session. So what's basically key to note is around 500 seconds, we do see definitely the drop in QoE that we noticed. We see drop frames and rebuffering kind of occurring like when we do see latency inflation. So like latency inflation is definitely so like we definitely do get like some kind of like correlation. And this is and it's definitely been like shown in literature. This was kind of just more of like a verification in our setup. Like, do we also see like similar things to kind of like what people have mentioned? Like and like there's definitely like correlation with these like latency inflations and reduction in QoE. But we definitely want to be able to understand better how we can draw some kind of conclusion from the UDP packets, whether it's like the data rate or maybe the inter-packet delay or like the size of like packet bursts. But that would be much better for quantifying the actual what might be more better, what might be better for quantifying the a finer grain quantification for the latency inflations, right? So if there's like an actual problem, then like maybe we'll see that with like the burst sizes changing more often. That's like what I was trying to say. So lastly, I just kind of wanted to talk about detecting ephemeral events. So ideally, like we wanted to see if there's some kind of predictability to all these like latency inflations, whether they happen like gradually or whether it's like kind of like instant. And so this kind of definitely shows that like these latency inflations, like they transition from a period of like normal to like not normal in a very, very short period of time. So like if we're kind of measuring the difference between 10 milliseconds and 100 milliseconds for like hosts that are experiencing latency inflations, this happens within like a couple seconds, right? So like you'll basically, it's not like it kind of like gradually increases from like 20, 30, 40, 50, 60, right? So that was kind of like the idea, which makes them very less predictable. So that's it's definitely going to be difficult, but this is at the host level, right? So what the next step I want to extend this to is like maybe we want to monitor things more at the access point level rather than at the host level, right? Because maybe the access point will have a better idea based on the number of hosts that are connected, and like the data rates that each of them are sending in. So so in general, future work, so in general, like I was saying, I couldn't really scale up the QoE experiments with the summer hitting because students have kind of left, so the latency inflations in like the library or like the university center are kind of like missing right now. But we're definitely going to scale up the setup now that like we've acquired more devices and like we're registering these devices with UCSB, so we can actually install them with PoE. And additionally, we want to debug that AMON issue I was mentioning where we can't see full visibility of the hosts. Like I was only able to get visibility in about half the hosts. So I want to like fix that so I can get full visibility. And so like some of the next steps, kind of like follow-ups to like what I talked about is ideally I want to be able to like use these kind of like latency, like I want to understand how we can like detect issues using UDP for hosts that are mostly sending UDP traffic, right? Because there's clearly not going to be enough TCP samples to have very fine grained detection for these issues. And so we need to use a different methodology. But than just TCP flows. And additionally, I want to break down the current RTTs that I have into like upstream and downstream so I can kind of understand where the issues are occurring, because I wouldn't expect these issues to be symmetric. I would assume that it's likely like the downstream RTT may be more delayed than the upstream, the downstream latency may be would be larger than the upstream latency. And so in such cases, there may be like more severe severely impacted clients, versus if the upstream was just delayed, because that's just carrying an app, right? Um, and yeah, and so and yeah, maybe follow-ups to the spatial nature as well, so we can better understand if we can predict which subset of hosts are like the actual causes and what these actual causes are, right? Because that would be very useful to actually improve the quality of the network. What if we can identify whether these are just like provisioning issues, or if they're like wireless issues that we like need to fix. Yeah. And so kind of like takeaways, bringing this back to like yeah, the things in like my proposal is like identifying a relationship between like QoE and like lightweight network metrics, right? So literature has definitely talked about latency being important, right? Because like buffer bloat and like packets are usually sent in bursts, right? So it's like bandwidth can sometimes be like misleading, like if an application thinks it has like more than it can actually use, right? When it like does that estimation. And additionally, like 95 percentile is a good indicator for congestion when we're like looking at like hosts. A lot of literature says like 99 for like flow level. But yeah, we use 95 in this for hosts, and it was able to yeah, find ephemeral events kind of like were correlated with reduction in QoE. And yeah, and yeah, 95th percentile is good because we're looking for inflations that are actually causing issues with applications, right? And applications basically have recovery mechanisms already that allow them to account for this, right? And so we're looking for inflations that could actually cause problems for these applications. And so additionally, like potential biases with MLab's active measurements, this one was add a little less for, but ideally we know that like these ephemeral events are short-lived. Like a lot of the issues that like students for sure like on UCSB's campus are like, experiencing are like less than 10 seconds at a time, right? So if they're trying to run tests like after experiencing these issues, like we need to better understand kind of that's kind of like the point of the analysis with interephemeral event duration, right? It's like how frequent are these users experiencing ephemeral events again and again? Because when they run these tests, are they actually going to get useful results that kind of indicate the quality of their network as the ephemeral event is going on, right? So that's kind of like the idea, and I'm still working towards that. So I hope to have more results on this, but yeah, that's kind of what I have to provide on that for now. But yeah, in general, that's all I have. A special thanks to like people in the SNL lab, just anyone who's like helped me along this way in the past 6 months. Very big thank you to everyone. And yeah, thanks.